again base 3. 2 plus imaginary 0 plus imaginary 0 is 2, which is now up to 3. So we'll write it instead. Remainder 1 plus 0 plus 1 plus 0 is 1. 1 plus 1 is 2. All these values are now up to 3. 2 plus 2 is 4. That's more than 3. 4 divided by 3 is 1. Remainder 1. We keep our 1 here. 1 plus 1 is 2. It's not up to 3. Then 1 plus 1 again is 2. And then 2. Base 3, which is our final answer. That's divide 11000 base 2 by 110 base 2. Everything we are going to do is in base 2. That is 11000. Yes, divided by 110. We are going to divide in base 2. What we are having here is that it's not possible to divide 1 by 110. It's not possible to divide 1 by 110, but it is possible to divide 110 by 110. So we are having 1 here. 1 times 110 will be 110. But then you subtract, you'll be having 0. Bring down this 0. Multiple, if you divide 0 by 110, you get 0. 0 times 110 is 0. By the time you subtract, you still get 0. Bring down this 0. Again, 0 divided by 110 is still 0. If you multiply, you get 0. And then it gives you 0. You have 0, which is our final answer. That means, therefore, 11000 is 2 divided by 110 is 2 is equals to 100 is 2, which is our final answer. The last question we'll be treating under number-based system is under division. We're going to divide 11 is 2 by 101. This is 11 is 2 by 101. It's not possible to divide this. So what we'll be having here is, on this one, which is possible for us to divide it, we'll be having 1. It's possible. That is 1 times 101 will be 101, which will be, when we subtract this, 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. We bring down this 1. 101 divided by 1 will give us 1. This 2. Then if you multiply 1 times 101, it will give us 101. On subtract, we'll be having 0. Bring down this 1. Is it possible to divide? This one is what we brought down here. Is it possible to divide 1 by 1? No. That means we put 0. 0 times 1 is 0. So we'll be having something like this. That's 0. That's 1. 1 minus 0 is 1. Bring down this 1 again. This 1 is what we are bringing down now. 11 divided by this is not possible, so we still write 0. 0 times 101 is 0. So we'll be having, again, we subtract, that will be 1, 1. And then we bring down this 1 to make it 111. 111 divided by 101 is 1. 1 times 101 give us 101. Subtract again, we'll be having 0, 1. 1 minus 1 is 0. So bring down the last one. 101 divided by 101 is 1. 1 times 101 is 101. Which gives us 0, 0, 0. No remainder. That is, it's a perfect. We are able to divide this set of figures by this without remainder. Therefore, we can boldly say, we can easily say that 1, 1, 1, 1, 1, 1, 1, 1 base 2 divided by 101 base 2 is equals to 1, 1, 0, 0, 1, 1 base 2, which is our final answer. Our next topic is modular arithmetic. Modular arithmetic is a form of calculation that occurs in a cycle. It has its application in areas such as analog clock, days in a week, months in a year, market transaction days, that occurs in a cycle. That is, when we have, there are some areas whereby they don't go to markets. That is, we don't have market transactions every day. That is, it occurs in a cycle, maybe a cycle of 5 days or a cycle of 7 days. And it's also useful when we are to prepare a chart for some people working on shift basis. Its calculation is much more similar to what was obtained in the number-based system. But the only difference is that concentration is placed on the remainder. That is, it's only the remainder that will be is much more important to us. For example, if the time is 8 a.m. now, and you are to meet your friend in the next 26 hours, when will you meet your friend? Now, if you are to add that, it's just 26 hours from 8 a.m. just now. The time now is 8 a.m. That is 8 a.m. and your friend is coming in the next 26 hours. Next 26 hours. Which means that we can just add it. 8 plus 26 will give us 34, which is not possible on our analog or on the wristwatch. It's not possible. What we have on the wristwatch for the digital watch, digital clock is 24 hours, and some clocks are being done in 12 hours. But for the analog clock, what we have is 12. Start from 12, which also can stand at 0. Then we have 3, we have 6 here. We have 9 here, and this 7, this 8, this 1, this 2, 4, 5, this 10, and 11. What we have been told, our longer arm is pointing to 12, and our shorter hand is pointing to 8. It's 8 here, which means that if we are to do it manually, we'll be counting. We have to count 26 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That is, our shorter arm will be pointing to 10. But for us not to go through the stress of counting like this, that is starting from 9 all over again before we get to 10. We can just say that since the divisions, we have 12 equal divisions here, which makes it, we can easily say base 12, but here in modular arithmetic, we don't usually make use of base. We don't call it base, we call it modulo. So we can just say that 8 plus 26 modulo 12, which is equal to 36. Our 36 is also equals to 34. It's the same thing as 12 times 3. 12 times 3 will give us, no, that's 12 times 2. 12 times 2 will give us 24. 34 minus 24 will give us 10 plus 10. Mind you, in the first statement I made, I said our concentration is based on the remainder, that is this. So we can now say that it's equals to 10 based on what I actually explained the other time. So we can just say that 10, it is 10 o'clock. Now, the bone of contention can now be, oh, is it AM? Is it PM? So we can just say that it's 10 o'clock.